In this video, I'll go through the non-inverting amplifier configuration. And in this configuration, you will see that the input voltage is connected to the non-inverting input. However, the feedback loop is still connected to the negative or the inverting input in here. And that's for a purpose for system stability. This is what we call negative feedback loop. So it has to be connected to the negative or the inverting input. Anyhow, so let me just highlight my assumptions. So my assumptions typically is the IN going in here is 0 and the IP in here will be 0. And that's basically because our input is infinity, okay? And then the other thing that we know now is VP happen to be just simply VI. That means VN is also VI because we have this virtual short between them. There's no short, it's just what we call it a virtual short. So I'm gonna just write these assumptions in here. IN equals IP equals 0. And in this particular case, the non-inverting input happen to be basically the voltage, the input voltage, and VN is also the same. Alright, so now what we need to do is we need to write, we have a node in here, we have another node in here, we have another node in here. I'll just write nodal equation in 2 because for 1 it doesn't make sense. I know all the currents. For 3 I don't know the current coming out of the amplifier, so that leaves me with 2. So let me just write a nodal equation at that particular point. So for that particular point, I will know that it's simply Vn minus 0 divided by R1 plus Vn minus V output divided by R2 just simply equals 0. But I know that Vn is just simply Vi, okay, divided by R1 plus Vi minus V output divided by R2 equals 0. And if we do the algebra, what we'll end up with is the following. We'll end up with 1 divided by R1 plus 1 divided by R2 all times Vi equals 1 divided by R2 times V output. And of course then the V output is just simply, if I multiply both sides by R2, you will see that will be R2 divided by R1 plus 1 Vi. And that's basically the relationship between the input and the output. And if you do divide both sides or by Vi, you'll get what we call the closed loop gain, and that's simply R2 divided by R1 plus 1. Alright, in this particular case, similar to the non-inverting or similar to the inverting case, you'll see that we have R2 divided by R1, but now we have a plus 1 in here in the gain. Okay, so the gain is always, regardless of whether R2 or R1 is smaller or bigger, it's always going to be greater than 1. So V output is always greater than the V input, regardless of the values of R2 and R1. Okay. It might be by a little bit if R2 is smaller than R1, or maybe a lot if R2 is greater than R1. And in both cases, I have a positive in here, so the V output have the same sign as the V input, and that's why we call it a non-inverting configuration. Alright, so before I move on to solving maybe a quick exercise on this, I just want to emphasize that there's another way we can solve this particular exercise, and that depends on the fact that IN is 0 in here. So if IN is 0, so technically the resistor R1 and R2 are connected in series, because the current that is going through R1 is the same current that is going through R2. Okay, I don't know the sign of the current, but if I assumed it to be this way and this way, that's how it will be. Alright. Okay, so what does that tell me? Well, guess what? I know that the voltage between here and here is just simply V out, and I know that these two resistors are connected in series. I can apply voltage division, and specifically to get this voltage in here, which happened to be the V input. Okay, so if I'm interested in getting what V input is, I will say, well, the source voltage across the both resistors is that, and the voltage I'm interested in is the one across the R1 divided by R1 plus R2, and then that means V output is just simply R2 divided by R1 plus 1 times V input, and that's exactly what we saw a few seconds ago. It's just a direct implementation just using voltage division. This is just voltage division rule, and we get the same exact answer in here. And here's a direct example of this non-inverting amplifier configuration. So what I have done is I provided the R2 is 10 kilo ohms and R1 is 1 kilo ohm, and I've also placed a load at the output of this amplifier, and I put a 1 volt at the non-inverting input in here. And I copied the equations that we got a few seconds ago, and what I'm asking you to do is actually to find the I naught in here. So the equation just gives me V naught, and as a quick reminder, we don't know what the I naught is coming out of the amplifier because it's coming from the power supplies that are powering the amplifier itself. So what we need to do is we need to probably just write a KCL equation in here. So by writing these KCL equation, we will have to pretty much figure out the IL, for example, and maybe this one here, which I'll call I2 since it's the same current that is flowing through here. So we write a KCL equation and compute the I2, compute the IL, and I'll be able to figure out what I naught is. So let me get started with that. So first of all, you can definitely start with assumptions that IN is 0, IP is 0, and of course this V here, which is VN, should be, well, the VP is 1 volt, which means the VN is also 1 volt in here because of the virtual short. Okay, so we pretty much know all the voltages that we need, and you can of course come up and write the equations or like write nodal analysis in here just to figure out what the V naught is, but we don't need to because this is just a very standard configuration, so we can just directly use the equation here. So in this equation, what you will see is the V naught is just simply R2, which is in this case is 10 kilo ohms divided by R1, which is 1 kilo ohm plus 1, times the V input, which is just simply 1 volt, and that will be just simply 11 volts. So the output in V output in here is just 11 volts. Okay, so we know the V output. Now all we have to do is just figure out IL, I2, and I0. What I will do is at the output, I'm just going to call this here O. At 0, let's do the KCL at that particular 0, and what we will get is the I naught plus I2, these are the current going into the node, equals IL, and what we're looking for is just simply I naught, which means it's IL minus I2. So let's try to figure out what the IL is. Well, IL is simply the voltage across this 2 kilo ohm is simply V out, which means that is 11 divided by 2, which is just simply 5.5 milliamp because it's 2 kilo ohms. And similarly, we can figure out what the I2 is. So let's take a look at the I2. So I2 is the current that is flowing from here to here. So technically, it is the voltage at this point minus the voltage at this point divided by 10. That's what we have to do. So let's figure out what this voltage in here. So the voltage, that's for I2. Yes. Yep. If we decided the I2 should be this way, yes. So we just put plus minus, and that will be here as the VN, which is basically the 1 volt, and this one here is a V output, which is just simply the 11 volt. So let me just make sure that this is actually the negative in here, okay? And this one here is V output, which is 11 volts, okay, and that's the negative. Okay, so the voltage across that is, the voltage across it is just simply 1 minus 11, which is negative 10. All right, so I2 is just simply VN minus V output divided by the R2, which is VN happened to be 1 volt, this happened to be 11 volt, the R2 happened to be, I believe, 10 kilo ohms, yes. So what we have is negative 1 milliamp. So now we take these two in here and we'll figure out that the I naught is just simply IL, which is 5.5 minus 1, which is 6.5 milliamp, and that's basically it. And of course, this is how I computed the I2. I could have also computed it using I1. So if I call this to be I1, it's the same current because this I1 actually goes in here. Since this is 0, it's the same as I2, and I can compute the I1 in here very quickly, and I1 will be simply the voltage across this 1 kilo ohm, and I know that the voltage in here is just simply 0 volts, and the voltage on this side is just simply 1 volt, okay? That's 1 volt, and the reason why it's 1 volt, it's because it's the voltage in here, which is VN. Okay, so that means it is 0 minus 1 divided by 1, which is just simply negative 1 milliamp, and that's pretty much what we found for the I2.